Hello guys, you are welcome to this lecture. Now this is lecture 2 of our biochemistry class, and we are also looking at carbohydrates. In lecture 1 we talked about the definition of carbohydrate, the classification of carbohydrates, and we enter into stereoisomerism in carbohydrates. Now let us look at what we have for today. Now what we have here for today, we have the review of the assignment. That is to say, we are going to look at the assignment we did in our last class. We are going to look at epimerism, which is epimers, enantiomers, diastereomers, and anomers. Now, there is no year that a question will not come under these topics. They are the first question you will see there after define carbohydrate whatsoever. What are epimers? What are enantiomers? And give examples. What are diastereomers? And give examples. What are anomers? Which of the carbon is the anomeric carbon of glucose, and so on and so forth. So let's look at the assignment we did in our last class. The assignment said define carbohydrate. Most of us got this correctly. I don't have much work to do here. Now the definition is carbohydrates are polyhydroxy aldehydes or ketone, or compounds that yields this polyhydroxy aldehyde or ketone when hydrolyzed. We say hydrolyze means to do what? To break something down. Okay. Now the next one is classify monosaccharides. Now this is where I want us to pay attention to, because I saw some of us writing some funny stuffs here. Now we said the classification of monosaccharides are classified in two ways. One, based on the functional group. Okay. We say we have classification based on functional group. Okay, now classification based on functional group. We said under this, what we have is we have the aldose, and then we have the ketose. Now, of course, you know the aldose are those ones that have the aldehyde functional group, and the ketose are those that have the ketone functional group. Now, I believe that ketone and aldehyde should not be something that we are going to be troubling ourselves with by now. We should be able to distinguish between a ketone and then an aldehyde. Now, the next one we said was based on, let me write it here. The next one was based on the next one we had was based on number of carbon. Based on the number of carbon. That was the next one we talked about. Okay. Now, we said based on the number of carbons, we have two, or we have different types. And I gave you something like carbon 1. I gave you something like carbon 1, carbon 3 rather, to carbon 7. Now in the exam, this is where I want to actually stress on. In the exam, don't go and write carbon 3 to carbon 7. Write the names. I gave you the names. We said based on the number of carbons, they are classified as trioses, which is carbon 3. Then what other one did we have? Tetrose. Are you getting it now? Pentose, hexose, and then the last one is what? Heptose. Okay, so based on the number of carbons, they are classified as trioses, tetroses, pentoses, hexose, and what? Heptose. Don't go and write carbon 1, carbon 3 to 7. You feel very well. Are you getting it now? Based on the number of carbon, you can write carbon 3 triose, carbon 4 tetrose, carbon 5 pentose, carbon 6 hexose, and carbon 7 what? Heptose. Now, the next question is, what are the simplest monosaccharides of biological importance? Everyone knows this: glyceraldehyde and dihydroxyacetone. I believe everybody got this correctly. Then the next one is name one aldose and ketose and draw their structure. You could decide to draw the structure of glucose for aldose and fructose for ketose. So that is a wrap on the assignment that I gave to us. Generally, the performance was okay. I give you 80% to all of you. You did extremely well. Then the structure of heparin, chondroitin sulfates, and the rest I gave to you. I'm going to talk about them, but not in this lecture. So let's go straight to what we have for today. Now, we are going to look at epimers or epimerism, okay? That is what we are looking at, epimerism. Now, we said epimerism is a phenomenon whereby a compound, in brackets sugars, have the same molecular formula but differs in the arrangement around one asymmetrical carbon. It differs in the arrangement around one asymmetrical carbon. Now, let's look at these two structures very well. Now, the first thing we need to know is what is the name of this structure. This is glucose. This structure here is the structure of glucose. And then this structure here is the structure of mannose. Now, what can we see about these two structures, or what can we say about these two structures? Now, these structures here, they have the same molecular formula. They have the same what? Molecular formula. And what is the molecular formula? Is C6H12O6. If you count the number of carbons here, is how many? 1, 2, 3, 4, 5, 6. Number of oxygen here is 6 also, which is 1, 2, 3, 4, 5, 6. The number of hydrogen, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then plus these two, making it what? 12. That is why 6 is H12O6. Now, if you count this one also, it's also the same. Now, we talked about a chiral carbon center or an asymmetrical carbon center as a carbon center that has 4 groups about it, right? Now, in the previous video, we also established that this carbon center here is a chiral carbon. Now, this is also a chiral carbon. This is a chiral. This is a chiral. But this first carbon and this first carbon is not a chiral carbon. And we said that glucose has how many chiral carbon? It has 4 chiral carbon. It has how many chiral carbons? 4. And we said that the number of isomers that glucose can form, number of isomer is given by 2 raised to the power of n. Number of isomer is given by 2 raised to the power of n, where n is the chiral carbon. So in this case, for glucose, n is equals to 4. So the number of isomer that glucose is going to form, it will be 2 raised to the power of 4, which we said is 16. That was for the first video. Are we getting it now? Now, if you have not seen that video, try as much as possible to see that, okay? Or that first lecture. So the epimers of glucose, these are the chiral carbons. Now, if you come here also, you agree with me that this is also a chiral carbon for mannose. Chiral carbon, chiral carbon, chiral carbon. Now, look at these two structures. What is the only difference you can spot in these two structures? What is the only difference you can spot? Now, you agree with me that the only difference here, if you look at the structure from up to down. Now, if we want to number, we number from here. This is our number 1. This is our number 2, number 3, number 4, number 5, and what? Number 6. The same thing applicable here. 1, 2, 3, 4, and 5. Okay, what am I numbering here? This is 1, 2, 3, 4, 5, and what? 6. Now you discover that at carbon number 2, the OH here is at the right hand side. Are we getting it now? And at carbon number 2 here, the OH is at the left hand side. Now, what conclusion can we draw from this? We would say that glucose and mannose are what? Isomer, because they differ in the arrangement of the OH around one asymmetrical carbon. It must be an asymmetrical carbon. Now, we already established that this is an asymmetrical carbon, which is carbon 2. If you look at the carbon 2, the only difference between glucose and mannose is that in glucose, the OH group at carbon number 2 is at the right hand side. While for mannose, the OH group at carbon number 2 is at the left hand side. Every other thing remains the same. If you look at it, this OH here, OH, H, everything remains the same. But the position of the OH group is what differs at carbon number 2. So we say that glucose and mannose are what? Isomer. At what position? Position number 2. So you can come here and say glucose and mannose are C2H12 epimers. Now, when you say C2 epimers, it means carbon number 2 epimers. So that is what epimerism is. So when you are asked what is epimerism, you say epimerism is a phenomenon whereby a compound sugar have the same molecular formula but differs in the arrangement of OH around one asymmetrical carbon. Just one. If it is more than one, they are no longer epimers. Is that understood? It must be only one. If the position of the OH group is different at 2 positions, then it's no longer an epimer. It's no longer what? An epimer. Is that understood? Yes. Do we have any question on that? No. So if you are given what is epimerism, you say epimerism is a phenomenon whereby a compound have the same molecular formula but differs in the arrangement of the OH around just one. You must take note of this. Around one asymmetrical carbon. Just one. Or you can say around one chiral carbon if you don't want to use asymmetrical. Okay? Now, let's look at another example. What structure is this? This is the structure of glucose. Now, what structure is this? This is the structure of galactose. Of course, we know that this is chiral, 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 chiral. This is chiral, this is chiral, this is chiral, and this is chiral. Okay? Now, we all know the numbering. This is number 1, number 2, number 3, number 4. Sorry, why am I always making this mistake? This is number 1, number 2, 3, 4, 5, 6. And here is 1, 2, 3, 4, 5, 6. Now, if you look at these two structures very well, these two things are the same, right? Is that not so? Now, this one, OH here, is also the same what we have here. Here is supposed to be black because I did differentiate them here. Okay, so let's not try and differentiate them with red. So this is OH here, OH here, they are the same. The position is the same. How about here? OH here, OH here, they are the same. Position is the same. Now, but when you come to carbon number 4, you discover something. That the OH here is at the right hand side, which is this red OH, right? While the OH here is what? At the left hand side. So this one is at the right hand side, while this on the left hand side. Now every other key remains the same. OH here, OH. So you see that at position number 4, the OH what differs. So when there is a difference in position at any of just one of the position, just one, on the asymmetrical carbon, we say that phenomenon is known as what? Epimerism. And then the two compounds are known as epimers. So when they ask what are epimers, you say epimers are compounds that are formed when compounds or sugar having the same molecular formula differs in the arrangement of OH group around one asymmetrical carbon. So these two are epimers. So you can now say that glucose and galactose are C4 epimers. The first one is glucose and mannose are C2 epimers. While here, glucose and galactose are what? C4 epimers. Is that understood? But galactose, take note of this, and mannose are not epimers. But galactose and mannose are not what? Epimers. Galactose and mannose are not epimers. Look at this structure very well. This is mannose. Now you discover, if I were to draw the structure of galactose here, let me draw the structure of galactose here. Now this is galactose. CHO. Then we have C. Here is OH. Here is H. Here is C. OH. Here is H. Here is C. OH. Here is H. This is, I mean, 1, 2, 3, 4. Okay. This is 1, 2, 3. Okay. Here is OH here. Yeah, it's correct. OH here. And then here is H. Let me try and get the structure before I mistake. This is galactose at carbon number 4. Okay, it's correct. Then we have the last one, C, second to last rather, OH, H, and then CH2OH. Now you must be able to memorize these structures. It's very essential. Now if you look at this very well, what do you notice? Between mannose and galactose, you discover that this OH here is different from where we have it here. So there is a difference here, okay? Now look at everything again. OH, OH, the same. But this one also is also different from what we have here. Are you getting it now? So both of them differs at 2 positions. Hence, mannose and galactose are not epimers. But glucose and mannose are epimers, C2 epimers, and then glucose and galactose are what? Epimers, which is C4 epimers. Is that understood? Now, let's forge ahead. So that is all you need to know about epimerism. If you are given any question on epimerism, you should be able to answer it now. It usually comes and they will say, oh, define epimers. You'll be able to draw structures to illustrate what you are talking about. Okay? Now, the next one is enantiomers. Now, enantiomers, these are stereoisomers that are non-superimposable mirror images of each other. They are non-superimposable. Please take note of from here down. They are stereoisomers that are non-superimposable mirror images. They are mirror images of each other. Now, what is a mirror image? For instance, let's say this is somebody. Assumption, okay? Me, I can draw. Wow. I'm very worst at drawing. Now, let's assume this is somebody. Now, what do you think would be the mirror image of that person? Something like this, right? Let's just assume. It's an assumption. What's the mirror image? It means that this one will be facing this way, while this one will be facing this way. That is the what? Mirror image of this person. That is what enantiomers are. They are stereoisomers that are non-superimposable mirror images of each other. They are also called D and L isomers. They are designated the 2 ways. The D way and the what? L. They are D and L isomer. Okay? D and L isomers. They are D and L isomer. And let me illustrate for you. Now, we have 2 forms, which I said is the D form and the L form. Now, how do we determine which is D and which is L? Now, this is the normal structure for glucose. This is D glucose. Now, you may not want to easily come to the assumption that this is D glucose. Do you know why? Because this CHO, everything follows. To determine if it is the D form or the L form, consider this penultimate carbon. When you say penultimate, it means second to last. Are you getting it now? Now, this is the first, second, third, fourth, fifth, sixth. This carbon here is the second to last. Are you getting it now? For glucose. Now, since it's the second to last, if the second to last carbon has its OH at the right hand side, you say it is the D isomer. So this one now is D glucose. Okay? Now, however, if the second to last carbon have the OH at the left hand side, it becomes L glucose or the L isomer. Let me take that again. Now, this is structure of glucose. Is that not so? If the second to last carbon has the OH at the right hand side, you say it is D glucose. If the second to last carbon has the OH at the left hand side, you say it is the L glucose. Is that understood? Now, I said they are called D and L isomers, and they are non-superimposable mirror images of each other. Now, can you still remember this structure? Let me draw a structure, if we can still remember. Can you still remember this structure? CHO, C. There we have OH, and then here is H, and then you have CH2OH. Now, what structure is this? This is the structure of glyceraldehyde. If you can still remember. Now, this glyceraldehyde, is it in the L form or the D form? This carbon 1, this carbon 2, this carbon 3. There are only 3 carbons here. Now, the second to last, of course, will be carbon 2, because we say second to last. It mustn't be carbon 5. So here, second to last is carbon 2. Now, since second to last is carbon 2, you now look at the position of the second to last. From there, you'll be able to determine if it is L or D form. Now, if you look, the second to last carbon has the OH at the left-hand side. So you say this is L-glyceraldehyde. Now, how about you see something like this? CHO, and there you have C. Here is OH, and then here is H, and there you have CH2OH. Now, the second to last carbon is what? Is here, and then the OH on that carbon, is it at the left or right? It's at the right hand side. So you say this is what? D-glyceraldehyde. Okay? So that is for enantiomers. Glyceraldehyde. That's for enantiomers. So enantiomers are superimposable. They are stereoisomers that are non-superimposable mirror images of each other. They are stereoisomers that are non-superimposable mirror images of each other. Okay? They are called the D and the L form. Now, you'll be able to determine which one is the D form and which one is the L form. Now, if you are asked what are enantiomers, you'll be able to write and also give structures. It's very, very important, pertinent. Okay? So that is for that. Now, let's move on to the next. The next one is diastereomers. Now, the term diastereomer is used to represent the stereoisomers that are not mirror images. They are stereoisomers that are not what? Mirror images. Now, we say for something to be a stereoisomer, first of all, it must have a chiral carbon center. Are we getting it now? So to determine if this one has a chiral carbon, now, if you know how to calculate chiral carbon, you agree with me here that this carbon here is a chiral carbon. Okay? Now, this carbon here is also chiral. Now, in the same vein, this carbon here is chiral, and this carbon here is chiral. You should be able to determine. We say chiral carbons are carbon center that have 4 different groups around it. Any carbon center that has 4 different groups around it, you should be able to know by now which is chiral, which is not chiral. I told you that this first one that carries CHO can never be chiral. Why? Because it has 3 groups around it. If you bring it down, something like this, C double bond O, H, and then you have this group here. This can never be chiral. Do you know why? Because this group here, 1, 2, double bond is considered as one group. So you have 1, 2, 3. It means that there are 3 groups there instead of 4. Instead of the normal 4, you have just 3 there. Okay? So this is not a chiral carbon. The first one is not chiral. Now, if you look at this one, this group here is different from this group here, right? And this group here is different from what we have here. And that group is different from this whole thing like this. You consider every other thing attached at each of these form bond. This 1 bond, 2, 3, 4. Are you getting it now? So all the groups attached, if they are not the same, you say this carbon is what? Chiral. That's why we say this one is chiral. Okay? Now, in the same vein, if you consider this last one, this one here, you agree with me that it follows the same portfolio. Okay? Let's try and examine it together. Now, you agree with me that what we have here, this O group from here like this, of course, no, we are considering this carbon, right? It's different from what you have here. And that is different from what we have here. And that is different from what we have here. So there are 4 different groups around it. So this carbon center is what? Is an asymmetrical center or a chiral carbon center. Now, this last one cannot be chiral. Do you know why? Because you have H2 here. H2 means there are 2 hydrogens attached. That is the meaning. And when you have 2 the same group attached, it means that the groups can never be what? Different. That means 2 the same group are present. And of course, for anything to be a chiral carbon, it must have all the 4 groups different Are you getting it? If one of them is the same, it means that it's not longer a chiral carbon. So this is not a chiral carbon. So in this case, now how many chiral carbons do we have? We have 2. Now, if I want to calculate number of isomers that it can form, it will be 2 raised to the power of n. And 2 raised to the power of n is 2 squared, where n is equals to what? 2 for 2 chiral carbon. And this equals to 4. Now, looking at these two, they are stereoisomers. But are they enantiomers? They are not enantiomers. Look at them. Say, you can just say that these are okay. Diastereomers is used to represent stereoisomers that are not what? In mirror images. They are not enantiomers, and they are not also mirror images. Now look at this. How do we predict that these are not enantiomers? Look at the OH group for both of them. They are the same position. Look at what we have here. This OH group, this is 1, 2, 3. And here is what? 4. We say the penultimate is used to determine, right? So penultimate here is second to last, which is third carbon. So in this case now, the third carbon here is what should have determined if they are enantiomers or not. Now, if you look at this also 1, 2, 3. The third carbon here should have been what will determine if they are enantiomers or not. But if you look at it very well, you agree with me that the third carbon have the OH group at the same position, at the same size. So these are not mirror images. Are you getting it now? And hence, they are not isomers. They are not enantiomers. Hence, you call them diastereomers. You call them what? Diastereomers. An example of diastereomer is D-triose and D-erythrose. Now, I have something to say here. Look at what we have in enantiomer. Look at something. Once the OH group is on the right-hand side for D-glucose, if you are coming here for N-glucose, everything that is here, listen very well. This is very, very important, okay? Since the OH group is at this right hand side, which is D-glucose. Now, if you are coming for N-glucose, everything that is here, including the OH group, will change position. To do what? We change position. Now, you agree with me that this OH group is at the right hand side, right? Now, this OH group is at the right hand side, okay? And since this OH group is at the right hand side, everything here, if you are coming to find the mirror image, that means the N-glucose. All you need to do, carry everything here to this side, including this other OH group. Are you getting it now? Including this other, the ones here, you must also change there because they are mirror what? Images. Are you getting it now? For instance, I was making reference to somebody facing this direction, and there's someone facing this direction. These are two mirror images. You cannot say, let this person's eye come here. If this person's eye come here, it's no longer a mirror image unless you change everything, including the mouth, the eye, and everything to turn this way. Same thing is applicable here. Are you getting this now? Since this OH is telling us that this is D-glucose, if you must convert it to N-glucose, everything here must change to the other side. So changing everything to this other side, you see that this OH here is now here. This H that was initially here is now at the other side. This OH now that was initially front here is now at the left hand side. Then this OH that was at the right hand side is now at the left hand side. So if you look at it, you see that this is like a mirror image. Is that understood? Don't just come here and change OH here, change the OH position and then leave every other thing. So persons, this is what they will do. Let me show you. This is what they will do. And if you do this, you fail. This is CHO, Abi. Then they will now do CH. They will say this is OH and then H, COH and then H and then COH and then H. Now they come to the penultimate carbon. What they would now do, they will now put OH here and then H and then C2OH like this. Is this what I taught you? No, this is not what I'm teaching you. Are you getting it now? Now, they will now say, okay, because this OH here is facing this side, then this is a diastereoisomer. This is an enantiomer. Is that what I told you? Now, if you do this, what have you done? You've done epimerism, because the only difference between these two is that the OH group at position number 5 here is different from what we have here. Are you getting it now? That is just one position for epimers. But when you're talking about enantiomers, since this one is OH facing this way, every other thing must come here. Is understood? That is the reason why we have this one like this. In such a way that everything that we are facing this way are not facing each other. Just look at the... Let me show you something. Look at this structure very well. Look at this structure I was using to illustrate for you. If you look at this structure, this is somebody's head, right? When the person turned, what happened? The head of this person, which is the back of the head, is now facing the back of the head of this person. So these two things facing each other are what? Alike. Same thing applicable here. These two things facing each other are what? Alike. OH, OH, HH, OH, 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 OH. Are you getting it now? That is for enantiomers. Is understood? I will also talk about diastereomers. We said this is a term that is used to represent the stereoisomers that are not mirror images. Example is D-triose and what? D-erythrose. Now you are going to do an assignment for me. You are going to do an assignment for me. It's a very simple assignment. The assignment says, what are the enantiomers of the following compound? What are the enantiomers of the following compound? You have D-triose and D-erythrose. All you need to do is give me their enantiomers. That means you give me the D form. This is already D form. Of course, everybody knows. Why? This OH is here. This is also D form. OH is here. Are you getting it now? What you are going to do for me is give me the L form. Give me the L form of it. Of course, everybody knows what to do. Change everything to the other side. Carry this one to this other side. I've given you expo, so I don't want to see nonsense. Okay? Thank you for that. Now, let's go to the next structure. Now, this was a something that was given to us in class, and most persons, they didn't, even me, I was confused because I didn't really take note of it. It came out in the test. Boy, say, draw the open chain formula, Fisher formula, and Haworth projection for glucose. Now, this is the structure of glucose. Now, this first structure you see here, all the ones that will be drawing since, you see this structure? All this structure that will be drawing since, all these ones, there are different ways in which glucose can be represented, but all the ones we'll be drawing since is called the open chain projection. It's called the what? Open chain projection. So this projection like this is called the what? Open chain projection. Or you can say open chain Fisher projection. But in the note, this is what we give to us, the open chain formula or the open chain projection. You can say open chain formula or open chain projection. Let's use formula, open chain formula, okay? So this is open chain formula. Now, in some places you will see it as Fisher projection, but he was trying to distinguish between them. So this is open chain Fisher projection, if you want to take it like that. Then this one is the Fisher projection, or you can call it closed ring projection. This is what he referred to as a Fisher formula. You can call it projection or closed ring. Closed ring. Now, what can you see here? The differences between these two. This one has already formed something like this, right? So this is the Fisher formula. Note the difference. I will tell you how these things came about. Okay? I will tell you how they came about. Now, the next one is the Haworth projection. Now, this is the Haworth projection. This is the what? Haworth projection. Haworth. This is the Haworth projection. Okay? This is the Haworth projection. So how did all this come about? And that brings us to what we call anomers. Now, let's take something very quickly, the chemistry of it. It said alcohol reacts with carbonyl group of aldehydes and ketones to form hemiacetyls and hemiketals respectively. Now, let me write this for you. What is the alcohol functional group? What is the aldehyde functional group? This is the aldehyde functional group, right? Arrow, double bond, O, right? Plus the alcohol group, OH. Now, let me do something quickly. Now ROOH. Now listen, this group here has a negative charge. It's a nucleophile. Now you must not really know this. When this nucleophile attach this, those of us in pharmacy, you should know this. This bond will come up, and then it's going to form something like this. Arrow C. Okay, let me use the necessary pen. It's going to form arrow C. Here will be O minus. Now, what happened? You actually attach this one with what? OH. Okay? And then at the end of the day, what is it going to form here? Here is going to give us H. And then this arrow here will become positively charged, because this arrow OH means arrow positive and OH minus. So this positive charge now will now attach here to form something like this. Now you don't really need to memorize how they got this. Now for ketone, it also follows the same procedure, but the only difference will be this. Ketone is arrow C double bond O arrow plus arrow OH. When this one comes here, this one packs up, and then you are going to form arrow C O arrow. Here becomes another arrow, and here becomes here will be OH, like that. So this one now is called the hemiacetal. When it is coming from an aldehyde, you call it hemiacetal, half of acetyl group. Then when it's coming from ketone, you call it hemiketals. Okay, but you don't really need to kill yourself with memorizing how we got this. Just know that alcohol reacts with carbonyl group of aldehydes and ketone to form hemiacetals and hemiketals respectively. Now, when you have done advanced organic chemistry, you understand how this process came about. Okay, now the hydroxy group of either the aldehyde or ketone functional group of monosaccharide can likewise react intramolecularly to form cyclic hemiacetals and what? Hemiketals. Now, what did we do here? You discover that we use the OH group to react with what? Carbonyl group, which is CO. Now, this is for two different molecules. Now, if we come to our carbohydrate, you see that our carbohydrates, they do what? They have a C double bond O group. True or false? They do. They have the carbonyl group. Are you getting it? Which is this. And they also have alcohol group, which is OH. So it means that the OH group of alcohol can react with the carbonyl group to form a cyclic structure. To form what? A cyclic structure. Now, this we convert to this, and this we convert to this. Now, there was a man called Haworth. Please take note of this. This is the most important thing you should take note of from here. Haworth proposed two structures. One, Haworth proposed two structures. Haworth proposed how many structures? Proposed two structures. One is called the Pyranose structure. Now, this is for cis-membered ring. That means the ring has 6 atoms in it. And then the next one he proposed is Furanose. Furanose has 5 members. Now, when you talk about 6 members, out of these 6 members from here, 5 are carbon, and then 1 is oxygen. Now, out of these 5 members from here, 4 are carbon and 1 is what? Oxygen. So please take note of this. Okay? 1 is oxygen, 5 is carbon, 1 is oxygen. For the 6-membered ring, what is it called? Pyranose. And then for the 5-membered ring, what is it called? You call it Furanose. Are you getting it? So when intramolecularly the aldehyde group and then the alcohol group of monosaccharide, they form intramolecular condensation reaction to form a Pyranose or what? A Furanose. Is that understood? Is that understood? Let me take it again. I said this group here is capable of reacting with this group here to form a cyclic structure, which is called the Pyranose or Furanose. Now, for this case, it is a Pyranose. Do you know why? Because it's cis-membered. If you count this carbon, what you have here is carbon, this carbon, this carbon, this carbon, this carbon, and then this is what? Oxygen. So how many carbons are here? 1, 2, 3, 4, 5. Plus 1 oxygen is how many? 6. That's why we say Pyranose has 5 carbon and 1 oxygen. So that is what you need to know about this. That the hydroxyl group of either, this is of either the ketone or, okay, the hydroxyl group or either ketone, not of. The hydroxyl or either ketone or aldehyde functional group of monosaccharide can likewise react intramolecularly to form cyclic hemiacetals and what? Hemiketals. Is that understood? Now, as time progresses, you tend to understand what we are doing here. Okay? Now, look at this very well. The pair of stereoisomers that differs in the configuration at the anomeric carbons are called anomers. The pair of stereoisomers that differs in the configuration at the anomeric carbons are called the anomers. Now, the first question you need to ask yourself is, what are the anomeric carbon? That's the question you need to ask yourself. What are the anomeric carbon? Now, in most cases, the anomeric carbon is usually the carbon with the functional group. The anomeric carbon is usually the carbon with the what? The predominant functional group. Now, look at this structure very well. Which of them is the predominant functional group here? We say this is the aldehyde because this is glucose and glucose is an aldose. Is that not so? That is it. So what carbon is this? This is carbon 1. If you want to number carbon 1. So this carbon with the functional group is called the anomeric carbon. It's called the what? Anomeric carbon. Is that understood? Now, in this structure, how do you predict which of them is the anomeric carbon? This carbon that is attached to this oxygen here is called the anomeric carbon. Take note. It's very important. They may give you structure. They will just say cycle the anomeric carbon. You should be able to cycle it. This carbon, let me take it again. Close to that is carrying this O here is the anomeric what? Carbon. Is the what? Anomeric carbon. This carbon carrying the O here is the what? Anomeric carbon. Do you know why? Because it is this carbon that was carrying the double bond here. True or false? If you look at it very well, this carbon is the one carrying the double bond oxygen. And we said the anomeric carbon here is carbon 1. So this carbon later condensed with this to form this. This is the anomeric carbon. So if they give you any structure and they say identify the anomeric carbon, first of all, look at the predominant functional group. We said there are 2 predominant functional groups in all carbohydrates. The 2 predominant functional groups are the aldehyde and the what? Ketone. So when they say what is the anomeric carbon, first of all, look for where the aldehyde functional group is. That position is where the anomeric carbon is. For the open chain projection or the, I told you different types of projection, right? Open chain formula or projection. Now, when you now come to the Haworth, the one carrying the oxygen here attached to this OH here is the anomeric carbon. So in this case, this is the anomeric carbon. Now, why did we not choose this as the anomeric carbon? Because this carbon does not have the OH attached here. Do we have any OH attached here? I mean, any oxygen, not OH, any oxygen attached here? No. Are you getting it now? So this cannot be the anomeric carbon. Now, there's a way they may draw it. They may draw it in such a way that you have O here and then every other thing continues. Are you getting it now? In this case, this carbon here that has this carbon attached to this O here is the anomeric carbon. So it can be in 2 directions. They may carry this one to this side and carry this one to this side. Just know that this carbon carrying the oxygen and then OH under is the what? Anomeric carbon. I've stressed a lot on anomeric carbon. Now, listen. The pair of stereoisomers that differ in the configuration at the anomeric carbons are called anomers. So you may be asked, define anomers. You say anomers are pair of stereoisomers that differ in the configuration at the anomeric carbon only. So we can say that anomers are also called epimers because they differ at only one of the carbons. Are we getting it? They differ at only one of the carbon. But let's not go just too much in details about that. Now, we say the pair of stereoisomer that differs in the configuration in the configuration are the anomeric carbons are called what? Anomers. They are called what? Anomers. There are two types of anomers. We have the alpha anomers. Please take note. And then we have beta anomers. How many types of anomers? There are two. Alpha anomers and then beta anomers. Now, which of them is the alpha anomer? And then which of them is the beta anomer? Now, most times, this structure you see here, we say is this Fischer structure. That is to tell you that carbon 1 here condenses with what? Carbon 5. Is that not so? So there's intramolecular condensation between carbon 1 and what? Carbon 5 to form this structure here. That's what I was trying to explain to you. Are you getting it now? Now, listen carefully. This structure you are seeing here, this structure, how do you now determine which of them is the alpha anomer and then which is the beta anomer? Let's think together. How do you determine which of them is the alpha anomer and beta anomer? Note that where you decide where you have the anomeric carbon is this, right? And they say a pair of stereoisomers that differ in the configuration and the anomeric carbons are called anomers. So the only place you should be looking at to determine the anomers are this carbon here, because this is the what? Anomeric carbon. This is the what? Anomeric carbon. Okay? Anomeric carbon. This is the anomeric carbon. Now coming here also, here's the anomeric carbon. This is the anomeric carbon. Okay? Now looking at this very well, you agree with me that the OH here is down and is opposite what you have here. The OH here is down and is opposite what you have here. Are you getting it now? The OH and this CH2OH are opposite each other. Now, predominantly, when you see that the OH is facing down, it's usually the alpha anomer. So in most cases, you will see some people, they will write this is alpha D glucose, because normally this is D glucose, right? This is D glucose. You know why it is D glucose, right? Because this OH here, this is the penultimate carbon. What condenses with this was the OH, right? The OH is in this direction. Is that not so? So we say this is D glucose from enantiomers we've learned before. Now this D glucose, this alpha anomer. So if you want to add it together now, since you know that initially this is D glucose, you now say this is alpha D glucose for this structure. Alpha D glucose. Now, how about this side? Whenever the OH is facing up, that means in the same direction with what you have here. Whenever the OH is facing up, that means in the same direction with what you have here. You call it the beta anomer. Beta what? Anomer or beta anomer. Now, this is also D glucose, right? So you call it beta D glucose. Beta D glucose. Now, do you notice something? Do you notice something? How do you draw this structure? How do you draw this structure? This structure, how do you draw it from here? Now, I want you to visualize something with your eye. Turn this thing in such a way that this part is facing down. If you turn it in such a way that this part is facing down, what do you see? Now, after drawing, in most cases, you'll be asked to draw this structure. Don't just memorize. Let me show you something. Or, I think memorizing will be good. But don't just memorize. After you must have drawn this outline out, which is this, what is it called? The structure like this. After you must have drawn this out, let me just show you quickly. This oxygen, you know that you must have this oxygen here. Now, how do you know the one that is up and the one that is down? Of course, you know that this one will be hydrogen, this CH2OH. Now, put in every other thing. Now, if you turn this thing down in such a way, visualize it like this O is sitting on the floor, like you have it like this. Visualize it like that. If you visualize this like that, you agree with me that this OH here, which is after this O, this other OH here, where is it facing? It's facing down. So you can now come here and say here will be OH because this OH here is facing down. And then if you visualize it like that, automatically everything here faces down, and then everything here faces what? Up. Is that not so? So if everything here faces down, so here will be OH, and here will be what? H. Now, we said everything here is facing down, right? Down. So we take it down. Why this one is what? Up. So everything here is facing up. So this one facing down now. This is OH. Now, here, what do you have here? H is facing down. And then what do you have facing up on this carbon? OH. Now, consider this carbon. What is facing down? OH is facing down. And then what is facing up? H. So you now see how they got this structure. Is that understood? You now see how they got this structure. Is that understood? They're coming here. This carbon also, if you look at it very well, you agree with me that if you turn it, it means that this one also is also facing down, right? So you have this as what? OH. And then here is what? Here is H. So you now see why this structure came, how this structure came from this structure. Okay? Now, similarly, if you also look at this one, we are assuming that everything here is facing down, and then similarly, we are assuming that everything here is facing down, and then this part is facing up. So if everything here is facing down, it means that this H also will also face down, which is this first one here. This is the first carbon, right? Which is what we are taking. This is the first carbon, okay? You understand? Okay, now, let me make it easier for you. Now, if you look at this very well, this is the first carbon you have here. This first carbon now is facing down. Why this other one is facing what? Up. Now, we said all of here is down, all of here is what? Up. So, we come to the second. After you must have drawn, you should be able to draw this outline now. This structure like this. It's very easy. Practice it, okay? Now, that will be one of our assignments. Are you, what am I drawing? I'm very poor at drawings. You should be able to draw it, just something like this. Oxygen, like this. And that is finished. Then you now put your lines like this, like this, like this, like this, and like that. So looking at this, I haven't drawn the outline. We said this one is facing, this is the first carbon here, which is the anomeric carbon. We said in this case, this is the what? Anomeric carbon. It's always carbon 1. So if this is carbon 1, this one is facing up, OH, and then this other hydrogen is facing down. Then we go to the next carbon. This is what? Carbon 2, which is this carbon here, carbon 2. Are you getting it now? This is carbon 2, this is carbon 2. Now, this one must face down, which is OH, and then this one must face up, which is what? H. Then we'll go to the next one, carbon 3. This is carbon 3. This one must face up, and then this one must what? Face down, because we say hydrogen is facing down. Now, coming to carbon 4, what do you think we face up, and which one do you think we face down? This carbon 4. Let's take it together. I believe you must be answering this in your mind now. Which of them do you think we face down, and which of them do you think we face up? Of course, OH will face down, and then H will face up. And then you now have this carbon. When you come to this carbon, this is always the setting, the arrangement. This first one, the hydrogen is always facing down, and then this O group here is always coming up. Is that not so? That is it. So, if I should give you any structure now, I believe we should be able to draw it, okay? For instance, or let's leave that, okay? So if I should give you any structure, that would be one part of our assignment. You should be able to draw it. Now, let's look at this. We said we have the Pyranose structure and the Furanose, right? Now, this structure like this for glucose is called the Pyranose. It's a 6-membered ring. It's called the what? Pyranose structure. It's a 6-membered ring. Furanose is how many member ring? 5-membered ring, which comprises of 4 carbon and 1 oxygen. Now, glucose is usually in the Pyranose form. Glucose is usually in the what? It's more stable in the Pyranose form. While fructose is more stable in the what? Furanose. So in most cases, they call it, if you want to call this structure now, you don't call it just normal glucose, you call it glucopyranose. Alpha D glucose what? Pyranose. And then this beta D glucopyranose also. Are you getting it now? Because this is the Pyranose structure, which is the Haworth projection. Now, there's another structure called the Furanose. It's a 5-membered ring structure. Furanose, fructose usually takes the Furanose structure. Usually takes the what? Furanose structure. Okay, this is the structure of fructose. We've not drawn fructose since. Now, fructose is a ketose. Do you know why? Because from here up is arrow group. From here is another arrow group. I will say when you have arrow, C double bond O, arrow. If I want to turn this, becomes C double bond O, arrow, arrow. This structure is called the ketone, keto. So fructose is a ketose sugar. Fructose is what? Ketose sugar. This is a structure. You should be able to memorize this structure. It's very easy. Now, the structure of fructose is almost the same like that of glucose. If you look at it very well, the only difference is this C double bond O here. And this, if I want to draw glucose, now glucose is just something like this, CHO. Then COH. H. CHOH. C. Now, it depends on whether it is the D form or the what? L form. Okay? Whatsoever. If it is in the D form, this one now is in the D form. If it is in the L form, it means this other one will come up this way. Okay? So that is that. Now, you see, or let me just finish it. This H, OH. This H, OH. Now, this is the structure of glucose. This is the structure of glucose. Now, what is different between glucose and this? You see that in place of this CHO, they just put CH2OH. Then, what you have here, you clean it up and then put double bond O. Is that understood? What do you have? Structure of what? Fructose. So from glucose, you can easily get fructose by changing the second carbon to double bond O, and then this first one here to CH2OH. Now, let's go to what we have, which is the business we have here. Now, what we have here is also the Pyranose form. The Furanose form of glucose. What we have here is the what? The Furanose form of glucose. Now, if you look at this is the Pyranose form, right? This is the Pyranose, this is the open chain progression, okay? Now, these two undergoes intramolecular condensation to form this oxygen here, okay? Now, with what we know, we said for Pyranose is 6-member ring, while Furanose is 5-member ring. Now, the 5-member ring is always like this. You have O, you have this, you have this, you have this, you have this, and then you have this. Okay? Now, in this vein, you also turn it upside down. Now, if you turn it upside down, what do you think you can see here? Okay, it seems there is a mistake here. Let me see. Okay, there's a slight mistake here. Now, when this undergoes the intramolecular condensation, here is supposed to be OH, okay? Because that will bring OH out from here. Like the way we have here. Look at the one we did here. When it undergoes intramolecular condensation at this point, what happened? OH came out. Same thing is applicable here. OH will come out, okay? Now, if you turn this upside down, according to what we already have the structure. Now, let us fill in. If you turn this upside down, this is carbon 1 now. In this case, this is carbon 2. Now, this is carbon 2. Are you getting it now? So what you are going to do is start to fill in. Now, in carbon 2, what do you think? If this is down and here is up, what do you think will be present in carbon 2? Up, up, up. What do you think is present for the first one? Carbon 2 is what? OH. So here will be OH. What do you think is present in carbon 2? Down. We said everything here is facing down, right? So what do you have here is CH2OH. Now, this other carbon here, what do you think will be down? Down is what? H. What do you think will be up? OH. Now, this other carbon here, which is the fourth carbon, this is 1, 2, 3, 4. Yes, the fourth carbon. What do you think will be down? OH. What do you think will be up? H. And then finally, this one is H, which is this H, and then CH2OH. It's usually in this form. You have C2CH2OH in Furanose. You have 2CH2OH. Now, look at it very well. It also follows the same procedure. Are you getting it? We have the alpha form and then the beta form. So which of them do you think is the alpha form here? And which of them do you think is the beta form? Now we said that when this one is facing up, what would you call it? You call it beta. Are you getting it? Why? If it is facing ground, you call it what? Alpha. So this is beta Furanose or beta D Furanose. Beta D fructofuranose, if I want to take it like that. Beta D what? Fructose furanose. We know why it is D, because of this OH is at the right hand side. So I believe that will be all for this lecture. So that is everything you need to know about Anomerism. Now, please make sure you submit my assignment before 3 p.m. tomorrow. It's very important. And then the next assignment is draw the Pyranose structure for glucose and then fructose. Are you getting it? Draw the Pyranose structure. So we have this first assignment here, and then we have the other one. Let me just bring them out so that we will not have any cause to complain. So we have this as our first assignment. What are the enantiomers of the following compound, which I've given to you before? And then 2, draw the Furanose and structure of glucose and the Pyranose structure. Are you getting it? Draw the Furanose structure of glucose and the Pyranose structure. 3, draw the open chain formula, the Fisher formula, and the Haworth projection for the following: glucose, fructose, and galactose. Okay? So that will be all for now. Thank you for your time.